Welcome back. Let's continue with our lecture on general theory of relativity. If you forget my name, I am Rajesh Naik from DPS IISER Calc. The videos are not coming very frequently. We have looked at the tensors, basic rules of tensors using the Lagrangian approach. So today we will formalize them with transformation rules, state some of the properties, work out some of the examples. So this is going to be listing out the properties of tensors and so on. So it is not going to be a very interesting lecture, as we are going to summarize mathematical object in a physics point of view. So the rigor going to be removed, and this is going to be mainly tensor analysis from the physics perspective. So let's continue with the lecture. Let's start with the tensor. We have already seen the definition of covariant, contravariant, tensor, metric tensor. Let's summarize all this, what we have already said about tensors, and state some of the more properties such that we can do some algebra with the tensors. When physicists look at the tensors, they're really looking at the properties of geometric object which transform under a specific way under a coordinate transformation. However, there is a full mathematical structures involved. We have already put a foundation to that, but we are not going in that direction. I have already told that given a coordinate system, you can have a basis vector, and based on that you can construct vector space, dual space, and multilinear mapping, which would be full formal mathematics of tensor analysis. But ever from physicists' perspective, it is sufficient to have the transformation property where we would like to define laws of physics in terms of tensors, and then we want to study how they change under the coordinate transformation. So our goal is to make a laws of physics invariant under the coordinate transformation using the tensor formalism. Here we generally have two coordinate system, which we call as O1 with the coordinate system x, and O2 with the coordinate system x prime, and then we look at various transformation. We have already seen that rank 1 contravariant tensor or tangent vector, the component of tangent vector ti transform with the following transformation rule under the coordinate system. The component t prime I in the x prime coordinate system is given by dx prime I divided by dxj tj. Here summation is done over the j, which is repeated over the contravariant and covariant, and then we get the component in t prime. So this is the relation between the components. Same way we can define first rank covariant tensor or a normal vector ni, which transform as n prime I in the x prime coordinate system is given by dxj divided by dx prime I and j. The summation is again over j, but with respect to x coordinate system here, and then we have a component in the x prime coordinate system. So we see that this is the basis of both tangent and normal vector, which are dual to each. One of the interesting property which is important from the physics point of view is when a tensor is zero, that's when it's all components of zero in one coordinate system, it is going to be zero in all coordinate system. It is trivial to see that if Tj is zero for all j in one coordinate system, ti prime will be also zero. Let's go ahead with the tensors and let's define the second rank tensor. The second rank tensor also we have already seen. The second rank contravariant tensor is like an animal which is having a two horns. So where each of these horns are like contravariant indices, and they transform independently irrespective of other as a contravariant vector. So two of them, the component a prime ij in x prime coordinate system is related to x coordinate system as dx prime I dxk into dx prime j into dxl into akl. Again, both these components k and l are repeated, and that is summed over. So you have two units of transformation which transform like a contravariant vector to give you a contravariant second rank tensor. We can also have a covariant tensor of rank 2. It's like an animal having a 2 legs. So each of these legs transform like a covariant tensor, that is B prime ij in the x coordinate system is related to AKL in the x coordinate system as a dxk by dx prime I into dxl by dx prime j summed over k and l multiplied by akl. So this is basically two covariant transformation converting a second rank covariant tensor from one coordinate system to another coordinate system. We can have a mixed rank tensor too. They are maybe look funny when you look them from the perspective of animals. It is like an animal having a one leg and one horn, but mathematically it is not so strange to build such things with the various indices. So mixed contra and covariant second rank tensor will have a one contravariant transformation and one covariant transformation as the rule for covariant vector and contravariant vector. 2 units of them make it a second rank tensor. We can also have a other way around. We could have a one covariant and one contravariant. If it is not symmetric tensor, they are not going to be the same, and you can have all higher rank tensor. So this is basically more properties of various tensors. So this lecture is going to be somewhat like a mass shooting of rules and relations of tensors under coordinate transformation, and this can at some stage get quite uninteresting. If the second rank tensor Aij is symmetric, then Aij is equal to Ajk. Now there is operation called the symmetrizing the second rank tensor, basically represented by round bracket around the indices, that is Aij round, that is symmetrization is equal to half Aij plus Ajk. We simply flip the indices and add them up. Naturally, a symmetrization operation only take the symmetric part of the tensor. So we see that for a given symmetric tensor, symmetrization on Aij is equal to Aij itself. One of the simplest example for the symmetric tensor is the outer product of a vector with itself. So you see that T is vector which is taken outer product with itself, then the order of multiplication generally does not matter, and you have a Tij is equal to Tji. So this way you are constructing a second rank symmetric tensor. Once we have seen symmetric, there is also anti-symmetric property, same way as matrices, because matrices can be mapped second rank tensor. So we have second rank tensor Aij is anti-symmetric if Aij is equal to minus Aj. So you flip the indices, acquire a negative sign. An anti-symmetrization, again there is an operation of a tensor which is represented by square bracket, that is tensor A anti-symmetrized with respect to Ij is half Aij minus Aj. For an anti-symmetric tensor, there is an error here, it should be anti-symmetric tensor. For an anti-symmetric tensor, Aij, the anti-symmetric Aij is equal to Aij itself. It is natural from the definition. Now one of the common examples for the anti-symmetric tensor is the Maxwell tensor in the electrodynamic. You have already seen that the Fij is equal to minus Fji. So it is basically comes as a gradient of a vector potential with anti-symmetrized already. So that is why it is an anti-symmetric tensor. Anti-symmetrization of a symmetric tensor, then you would get 0 because it's already symmetric. Same way, if we do take an anti-symmetric tensor Aij and then symmetrize, we are going to get 0. Let's go ahead and look at the metric tensor. The metric tensor we have already defined with respect to Lagrangian in the generalized coordinate system. It is given as a L is equal to Gij xi dot I into xi dot j. So this defines the kinetic energy. Also we have seen that the once you have the metric Gij, you can define the displacement. A metric tensor is a covariant second rank tensor, define length element in that coordinate system, that is ds square is equal to Gij dxi dxj, where the dxi is a small distance element. We have been given covariant second rank tensor. We can construct contravariant second rank tensor with a unique relation, that is contravariant metric tensor is given as an inverse of a covariant metric tensor, that is contravariant Gij into covariant Gjk is equal to delta Ik, where delta Ik is identity matrix. So this defines the relation or a unique relation between the covariant metric tensor and contravariant metric tensor. We often need them to do operation called the contraction or the taking the dot product. So we have seen that the pk as defined as a gki x dot I, we know that the x dot I is a contravariant vector, and we have seen that vector pk have to be covariant vector. That basically means that you can take a dot product of contravariant vector with the covariant metric tensor to give a covariant vector component. So this relation is coming uniquely from what is known as a dot product in the metric space. Metric space has a unique dot product defined through the metric, that is if you have a vector, the length of that vector t square is given as a gij, ti, tj. Now with the relation between the covariant and contravariant metric tensor as the inverse of each other, it also defines the unique relation between the covariant tensor and the contravariant tensor. So we can write length of vector t square as a ti upper and ti lower, that is also equal to gij, ti upper and tj upper, and same way that is also given as a contravariant gij taken the dot product with the ti lower and tj lower. So this defines as a unique relation between given a covariant vector to contravariant vector and given a contravariant vector to a covariant vector through the metric or the dot product between the two vectors. So it is unique nature of a metric space, what we call is a specific class of vector space, and then you can have always define this unique relation between the covariant and contravariant vector. So that is covariant ti is given as a dot product between the covariant metric tensor and the contravariant vector ti. Same way we have relation contravariant ti is given as a dot product between the contravariant gij and covariant vector tj. So this relation is unique and specific to the metric space. You can extend it to all the tensors and you can relate any covariant component to a contravariant. Let us get higher rank tensors. So these are usually animals with the more legs and more horns. So you may or may not see them in reality, but mathematically it is very easy to define them. A mixed rank tensor in the upper and lower with the specific rank will have that many indices. For example, Tij is a 6th rank tensor with 3 contravariant component ijk and 3 covariant component pqr. Each of these components would transform in their own way. All the contravariant indices will transform as a contravariant vector. All the covariant indices transform as a covariant vector under the coordinate transformation. So for example, this vector tijk pqr is given as a 3 contravariant transformation and 3 covariant transformation taken the dot product with the vector itself. So this can be easily generalized to arbitrary coordinate system, and given any higher rank tensor, one can also change the indices from upper to lower, contravariant to covariant, by taking the dot product with the metric tensor. For example, if you have a second rank contravariant tensor, you can take the dot product with the 2 covariant metric tensor to convert it to covariant second rank tensor, and this can go on with the arbitrary thing. So you can do second rank covariant tensor to a second rank contravariant tensor by taking dot product with the 2 of the contravariant metric tensor. There is another scalar which is quite interesting, which is called the trace. Trace are very useful even in the matrix analysis. Here, trace of a tensor is basically dot product summed over with the covariant and contravariant component. For example, if you have a second rank tensor Tij, the trace T would be given as a G contravariant Ij into Tij covariant, or Ij covariant into Tij contravariant, or you can have a Ti Ti. Because covariant and contravariant indices are repeated, that means it is summed over. That is what trace is, a sum of all diagonal element, and that is very useful entity. So you see that raising and lowering indices of a tensor is very common, and relativists are very fond of it. It is their routine exercise. Daily calories are burned by raising and lowering the indices to remain fit always in the tensor analysis. Now let's go ahead and let's see something very important, what we call is a Levi-Civita symbol. So it is naturally called a symbol because it may or may not be a tensor. In fact, it is not a tensor. That's why we generally don't call it as a tensor, but sometimes there is a misnomer also calling them a tensor. That is maybe called a slip of tongue. Calling everything with the indices as a tensor is also could be a bad habit. So the permutation symbol epsilon ijk or Levi-Civita symbol take three numerical values 0, 1 and -1. In the three dimension, they are represented by three indices epsilon ijk. Here you have a contravariant indices. You can also have a covariant indices by putting them all down. So the rule is that the elements are 0 if two or more indices are equal. That means if you have epsilon iik, then it is 0, or epsilon 112 is also 0 in the same way. That means if any two indices are equal, then the component is 0. If the indices ijk come as an even permutation of 1, 2, 3, then they take a value of 1. The even permutation is usually rotate this 1, 2, 3 in the counterclockwise direction. That is basically is the notation. Now comes the value of -1. It is if the indices ijk comes as an odd permutation. That is odd permutation of 1, 2, 3. The odd permutation means that the rotating indices in a clockwise direction or flipping any of the indices. For example, 1, 3, 2 is a odd permutation. That is because you have flipped the indices or rotated in a clockwise direction. Now with that we have epsilon 111 is equal to epsilon 112 or epsilon 113 are all 0, and we have many such components. Other thing is that we have a even permutation, that is epsilon 123, epsilon 231 and epsilon 312 are all 1. The another way to visualize them is to write 1, 2, 3 and then rotate them in the counterclockwise direction to get the cyclic permutation. So you can use 1, 2, 3 or you can use 3, 1, 2 or you can use 2, 3, 1. Any of these would give epsilon ijk 1. So you also have a counterclockwise rotation or odd permutation in which you have ijk, you rotate the indices in the clockwise direction. That way you get epsilon 1, 3, 2, epsilon 2, 1, 3 or epsilon 3, 2, 1 are -1. That comes from 3, 2, 1, 1, 3, 2 and 2, 1, 3. So they are all clockwise rotation of indices 1, 2, 3. So this way we can obtain the various values of the Levi-Civita symbol. One of the point to think here is what happens to epsilon ijkl. Why we have written with the epsilon ijk or why not epsilon ij? So in three dimensions. So that is a thing which you need to see. I may or ask you during your interaction. Now let's look at some of the properties of epsilon ijk or Levi-Civita symbol, and let's see why they are so important or useful. So one of the important property is a dot product between the two epsilon ijk. For example, epsilon iab dot epsilon IPQ, so naturally it comes with the co and contravariant, is given by delta AP into delta BQ minus delta AQ into delta BP. So this is a relation. So you can evaluate this by using the properties of epsilon ijk and all that thing, you would get this relation. However, it is good to remember them. We are not going to derive this from any first principle. Even if it is possible, it is not, may not be very useful. So we will come back to this. So once we have general product between two of the epsilon ijk, then we can contract and can get the lower one, that we can state it later. But this general way of remembering is that if you have a first indices taken the dot product, then you have AB, which comes in the same order for the first term and the second term. In the same way, the lower indices, first term comes in the same order, and then with the minus sign, they are flipped the indices. So this is a general way of remembering. It's fairly straightforward to remember this. It's fairly useful also, and that is why it is good to remember. From the above, we can also get epsilon ijb into epsilon ijq. So we have to take the dot product between the A and P. Once we do that, we can see that take this relation directly and take the dot product, replace P by J, and same way we can replace A by J and P by J, and then simplify. So delta Jj, we know that is equal to 3 in 3 dimension, and then delta BQ remains same, and then we have dot product here, which is essentially taken contraction between 2 delta ij, that is also equal to delta ij. So this essentially leaves 3 delta BQ minus delta BQ, that is equal to 2 delta BQ. So we can also show that epsilon ijk into epsilon ijk is equal to 6. Contract this identity and we can easily reduce that, because delta I is equal to 3, and this way we can get the properties of a delta ij.
Oh, there seems to be some problem with the animation system.
Let's anyway do some vector algebra with this toys which we have newly acquired. So our game here is reduce the sum of the vector identities, which involves the cross and dot product of a vector using this index rules or tensor rule. This is like using a sledgehammer or Thor's hammer to drive a nail. In the process, you might break the wall, but still these are interesting ways of doing vector algebra using the tensor notation. So for example, let's first define the cross product between the two vectors. Ith component of that, A cross B, is given as epsilon ijk aj bk. How to check this? You can substitute the value and see whether you get the same thing or not, and that should satisfy your curiosity that this in fact gives you the necessary definition. Now what we are going to show is that one of the most trivial result, B cross A is equal to minus A cross B. So let's start with the B cross A, ith component, that is given as a epsilon ijk bj ak. So this is the definition of B cross A. So we have a I, second index goes with B and the third index go with A. Now here in the next step we flip the index j and k in epsilon ijk. That we can always do. Epsilon kj is equal to epsilon ijk is equal to minus epsilon ikj. So once we do that, we get this result. But you see that the second index here goes with the A and the last index goes with B. So that is happens because we have only flipped the indices. We know the rule of how to flip the indices of epsilon ijk, but not A and B. Now we can simply rewrite here k and j are dummy indices. There is no need to call them as a j or k or k or j. It does not matter. As long as both these dummy indices are replaced with the new indices, you are fine, and then that would lead to the term becomes minus epsilon ijk b k a j. Now we convert this into vector equation. This is equal to minus A cross B. This is equal to minus ith component of A cross B from the definition given here. So this is how we show that the B cross A is equal to minus A cross B. Now we have defined all the time using the contravariant. We can also have a covariant component, that is A cross B of a covariant component is given as epsilon ijk. Now it comes as a covariant component. They also have a same rule. Contraction is only given in terms of delta ij, and then we see that covariant component of A cross B, ith component is given as epsilon ijk aj bk. So this is a definition. So we can go on and do more examples. One can get addicted to this silly method. However, it is useful. If you are not able to remember the complex vector identities, it is possible quickly to derive them. Though here, when I am doing it is step by step, but you can see that steps can be avoided and one can simply get the result very quickly. Let's look at the vector identity A cross B cross C. This is one of the painful one. One often needs it, but one doesn't remember what it is. So let's start with the A cross B cross C, ith component. That is, we treat B cross C as single vector. So from the definition, we get is this as a epsilon I j k A j and B cross C k. So that is because kth component of B cross C. Now again, the B cross C can be again expressed in terms of epsilon I j k, which results in the epsilon I j k A j epsilon k L m B L C m. Some of them come in the lower index, some of them come with the upper index. It doesn't matter. We know how to go from one to another. When there is a dot product, we don't have to worry because we get one covariant and contravariant metric tensor each, which cancels out to giving delta ij, and that we can easily go up and down if there is a dot product. If we don't have dot product, then we have to multiply by metric tensor. We can factorize the term. We can write epsilon ijk together. Here, see that the ijk and klm. So the dot product is not between the first upper and first lower index. It is between the last upper and the first lower. But we do not know the rule to that, but we can find out using our cyclic permutation. That is, we write ijk on a clock and then rotate it in an anti-clockwise direction, and then we know that the sign remains same. From this, we can see that ijk can be easily written as a kij without changing any sign because it comes in the cyclic order. So we get the result as a epsilon kij into epsilon klm into aj, bl and cm. Now we can use our identity which relates dot product of epsilon ijk in terms of delta ij. That is, basically we have delta il into delta jm minus delta im into delta jl and aj, bl, cm. Now we can pull in the quantities inside. We have deltas there which can be easily handled. So bl becomes bi from the operation with the delta il. Same way, Cm becomes Cj for the first term. Same way for the second term, M becomes I, so we have Ci, and L becomes J, so we have Bj, and Aj remains outside. We can pull in Aj also, then we get Bi, Cj, Aj, and Ci into Bj, Aj. We can write back into the vector notation. So what we have here, the component I of B vector multiplied with A dot C, and the second term is the ith component of C vector, that is vector C, and the dot product between the B and A, that is A dot B. So this way we can simplify a more complex vector relation using a tensor identity. It's a main reason using the tensor in relativity, because even the complex operations, to some way they get simplified. If we had to use vectors, then this would get extremely complicated. So we can go on, do more and more exercise. Let's do one more example. So this is a simple expression. This is a scalar. You got to simplify A cross B dot C cross D. It's a scalar. So you simply have to write down A cross B, ith component, and take the dot product with the C cross D with the ith element. So that we express both A cross B and C cross D in terms of epsilon ijk. That is, we have epsilon ijk, aj, bk, epsilon I, pq, cp, dq. Now there is no problem. First I and the first I getting contracted, and that we can easily write in terms of delta ij. That is delta jp, delta kq minus delta jq into delta kp, and then whole thing is multiplied by aj, bk, cp and d. Now we can pull in corresponding quantities inside and then do the operation with delta ij. The j becomes p. That means we are taking the dot product between A and C, and k becomes q. That means we are taking dot product between the B and D. That is the first term. And the second term is we are taking the dot product between A and D and B and C. So that is the dot product. So here we have the expression AP, BQ and CP and DQ minus AQ, BP and CP, DQ. we can write back in the vector notation, and then what we have is a dot c, that is what we have, and then multiplied by b dot d. In the second term, first thing is what we have is a dot d, that is a dot d, and then b dot c and the b dot c. So this way we can simplify various vector algebra using the epsilon ijk. Now we have a homework. Here I am going to ask you to do a slightly different kind of calculation. We know that gradient operation or d phi by dxi on a scalar can be represented by delta or nabla. Delta I is a component. It can be simply treated as a vector when it comes to tensor algebra. So it is a differentiation that we have to keep in mind. Otherwise, it simply acts like a vector with the component delta I. For example, the symmetric property of partial differentiation, that is, if we write del square phi by del x del y minus del square phi by del y del x is 0, that is a partial differentiation commutes with each other. That identity is basically written as ijk becomes a component, that is xyz, but we can simply write as ijk. So delta I delta j minus delta j delta I is acting on phi is 0. This is usually called the nabla, not delta, but yeah, we can confusingly misuse the notation. Standard vector differentiation, for example, divergence of vector v can be written as a del dot v, which is del I vi. That looks like simply a dot product between the del operation and the vi component. Same way, we can also have a gradient of scalar, that is simply delta phi. So delta is a component for that operation. So same way, curl is a cross product between delta and v. So we have epsilon ijk delta j vk. So this way we can use all our identities with epsilon ijk and simplify even the differentiation gradient and all that thing using our new notation. So in the homework, you are supposed to simplify that del cross v. So you might have done this several times. This is a very important vector operation which comes in the electromagnetic theory, which basically says the relation between the vector wave equation and its component. Same way, we can have a del dot a cross b, and another operation is a del cross a cross b. So these operations or these equations you have to simplify using the epsilon ijk property or tensor notation. You have 1 week to solve this and upload. So we have already had enough indices raising and lowering. Today's calorie has been already spent useful way. Let me stop here and we will continue with the next lecture.